So engine balancing, we started discussing yesterday, right? The topic of engine balancing. So what are the two balances that we have to consider in an engine?
Power balance and mechanical balance.
Yes. So first one is mechanical balance. So what does mechanical balance stand for? What do
Like
you mean by mechanical
vibrations,
balance? Huh?
like to minimize vibrations, or
Yeah,
like
all
when
the moving parts, right? All the moving parts, they counterbalance each other. So moving parts counterbalance each other, minimizing the vibrations. Right? That is called mechanical balance. So, when we consider mechanical balance, there can be two types of forces. One is called as the primary inertia force. What is this primary inertia force? What is the primary imbalance or primary inertia force that are there in an engine? Yes?
the components that are at rest, like initial force required to like overcome that.
Yeah, that is okay. But we are talking about imbalance. So, in terms of imbalance, what are the primary inertia forces? Imbalance forces. You're right in one sense, but where exactly do we see what causes this primary inertia force? It's not just the components at rest. Primarily, what kind of components the inertia forces, primary inertia forces, you know, um, are caused by? So you can say imbalances in rotating components. Primarily, what? The crankshaft. The crankshaft keeps rotating, right? So if there are imbalances in the crankshaft due to the rotation of the crankshaft, those are primary imbalances. For example, for every rotation of the crankshaft, just a moment. Yeah. So these are primary inertia forces, right? Primary inertia forces are caused due to the rotating components. Primarily the crankshaft, the shocks, the connecting rod has to move down and up. So sudden change of direction is there, and also due to rotation. That's why you see there are counterweights on the crankshaft. You have seen counterweights on the crankshaft, right?
Yes, sir.
So the counterweights are added to minimize the primary inertia force. Also, the flywheel is there to minimize the primary inertia forces. A large flywheel is kept to minimize the flywheel take care of many of those things. And then what about secondary inertia forces?
Sir, acceleration of the piston.
it's not acceleration of the piston. It is caused due to the angularity of the connecting rod. The piston acceleration is there, but then what causes the imbalance? The secondary inertia forces, the imbalance is caused due to the angularity of the connecting rod. We will discuss how that is. It is caused due to angularity of the connecting rod. Right? So that talks about mechanical balance. In mechanical balance, you have primary inertia forces and secondary inertia forces. So all of you must have balancing of rotating masses. You have learned in what, dynamics of machinery. Have
Yes,
you
sir.
learned? So how the rotating masses are balanced? How the rotating masses are balanced? Very simple. Anyone can say.
Counterweight.
Yeah, you add counterweights exactly opposite at the same distance, right? From the axis, right? So that is primary inertia force when you balance the. There is also, just a moment. There's also something called a static and dynamic balance, right? Static and dynamic balance. What is the static balance and dynamic balance? So now let me draw. Let's see. So if I consider a rod, okay, and let's say there is a certain mass A1, okay, and then I have a similar mass A1, and then you have a mass B1 and similar mass B1. This is, let's say, case 1. I'll take case 2. A1. So what's the difference between these two cases? Yeah, case 1 and 2.
First one is both static as well as dynamic balanced. Second one is only static balanced.
Yes, there's no dynamic balance. There's no dynamic balance because though the counterweights are opposite to each other, but they are not in the same location of the axis of the shaft, right? Though the counterweights are opposite to each other, they have static balance. 1 and 2 both have static balance. But 1 has dynamic balance also, but 2 doesn't have dynamic balance. Because the counterweights are not on the same location of the axis, they are separated from each other. So still there will be dynamic imbalance. of the shaft, right? So there will be dynamic imbalance. So this is about static and dynamic balance, even within mechanical balancing. So you have to understand within mechanical balancing, there is static and dynamic balancing involved, and also there are primary inertia forces and secondary inertia forces. So as long as the shocks that are experienced by the crankshaft are balanced by counterweights for the rotation of smooth rotation of the crankshaft, then primary inertia forces are taken care of. But secondary inertia forces are caused due to the angularity of the crankshaft. What is this angularity of the crankshaft? I'll just show you one diagram that will make things clear. So usually primary inertia forces are larger in magnitude. So if you take care of them, most of the problems are solved. But still, secondary inertia forces can also create lot of imbalances in the engine and vibration, consequent vibration. Now look at the diagram on the left side. Are you able to see what's there on the screen?
Yes, sir.
Yes, sir.
Yes, sir.
Yeah, so there is a cylinder and piston. So the length of the connecting rod from the piston is 8 centimeter. And then the crank throw, we call it as crank throw, right? The distance from the crankshaft axis to the connecting rod axis, that is called as crank throw, correct? Am I right? Or am I making a mistake? Can someone confirm me? Is the 2 centimeter called as crank throw? No answer.
We didn't get that, sir, but we call that as crank.
Yeah, it's called as crank throw. That's what I thought anyway. Okay, at least for this lecture, I will call it as crank throw. You go and check whether that is called as crank throw or not. Okay. So that 2 centimeter is the distance between the crankshaft axis and the connecting rod, big end of the connecting rod axis. Correct? That much you can understand, right?
Yes, sir.
So that 2 centimeter length is what is going to keep rotating, and that 2 centimeter becomes the radius of the circle. Correct? The 2 centimeter becomes the radius of the circle. So the total length is 10 centimeter. That is clear, right? That diagram is clear. Any questions on that?
No, sir.
No. Okay. Now, let's say the piston moves down. During power stroke, the piston moves down, right? When the piston moves down, let's say this crank throw becomes horizontal. Crank throw becomes horizontal. By what amount the piston would have moved down? By what amount the piston would have moved down?
Stroke length?
Huh?
Stroke length?
I didn't get you.
So the stroke length?
Tell me, na. So I've given you the numbers here: 8 centimeter, 2 centimeter, 10 centimeter. By what length the piston would have moved down when the crank throw is horizontal? I've shown you a horizontal crank throw there, right?
2.25, sir.
2.25.
2.25.
Why it is 2.25 and not 2 centimeter? See, it's the crank throw is 2 centimeter vertical. Now it has become 2 centimeter horizontal. So 2 centimeter should have come down, right? Why it is 2.25? Why not 2?
Well, because connecting rod is somewhat angular, so like it is moved down by distance greater than 2 centimeter. It should.
Yes. The connecting rod is not vertical. The connecting rod has a certain angle. So it is moving at a certain angle. So the 8 centimeter is not the vertical downward movement. Only if the 8 centimeter has moved down vertically, then the piston would have moved down by 2 centimeter vertically. But the connecting rod is in a certain angle as it is moving down, right? Because of which the piston moves down by 2.25 centimeter as the crank throw becomes horizontal. Are you able to get the idea?
Yes, sir.
Yes, sir.
So draw the right triangle, you will see how the movement happens. So now when the crank throw from the horizontal position becomes vertically down, right? It is horizontal now, it becomes vertically down. Now what is the movement of the piston downward?
4.
No. Tell me from 2.25 how much it will go down further. From this position, how much further it will go down?
1.75.
1.75.
1.75 centimeter. So this is very important. Just carefully pay attention. So now imagine a full circle, okay? Now look at this, stroke length is 4 centimeter, that is total stroke length. But distance moved down by the piston is in first 90 degree of the crankshaft rotation is not 2 centimeter, it is 2.25 centimeter. That's what we discussed, right? And you're all clear why it is 2.25 centimeter, right? Does anyone have any doubt on that? How it is 2.25 centimeter and not 2 centimeter? I hope that is clear.
Yes, sir.
Yeah. And distance, so in the first 90-degree rotation of the crankshaft, so the crankshaft is like this. So first 90-degree rotation of the crankshaft, you have piston moving down by 2.25 centimeter. The next 90-degree rotation of the crankshaft, the piston is further moving down by 1.75 centimeter. So the stroke length is still 4 centimeter, but first 90-degree accounts for 2.25 centimeter movement of piston. The next 90-degree accounts for 1.75 centimeter of the piston movement. So that's what we have written here. So now imagine one full circle, that's 360-degree rotation of the crankshaft. What happens? Look at the upper 180-degree. Am I still connected?
Yes, sir.
The screen is not moving, right? Is it stuck?
Yes, sir. Screen is stuck.
Why it's happening? I don't know. Yeah. So now it's visible, right? Is it visible now?
Yes,
Yes,
sir.
sir.
Yeah. So consider one full rotation. So this circle represents one full rotation of the crankshaft. So you see top half 180 degree and bottom half 180 degree. So I've written on the top fast and bottom slow, right? So in top half 180 degree, piston travels more distance because 2.25 centimeter down and 2.25 centimeter up. If you consider the top 180 degree movement of the piston from left to right. But the bottom, it goes only 1.5 centimeter down and 1.5 centimeter up, the piston movement. Is that clear how it happens?
Yes, sir.
Yeah. So the piston travels more distance in the same time. It doesn't take different time. In the same time, the piston travels a larger distance in the top 180 degree and shorter distance in the bottom 180 degree. So obviously, in the top 180 degree, the piston moves faster, and the bottom 180 degree it is slow. Why this difference happens? Faster movement of the piston in top 180 and slow movement of the piston in bottom 180 degree. Why is this difference happening? Why is it traveling different distances?
Angularity of
Angularity of the connecting rod. Exactly. The angularity of the connecting rod is leading to this difference in movement of the piston. So obviously what happens in one full rotation, the piston is not moving with uniform velocity through the entire 360 degree. First half rotation, it is moving at a faster pace, and second half it is moving at a slower pace. So this also develops inertia forces, right? So this is called a secondary inertia force. So you can't get rid of this so easily, the secondary inertia force. Do you understand what's the secondary inertia force now? Is it clear?
Yes, sir.
Yeah, so this is secondary inertia force. Primary inertia force are only due to the rotating masses which you can easily counterbalance by adding weights. You can balance by adding counterweights, I mean. But then for this, it's so difficult. How can you overcome these secondary inertia forces? You can minimize the imbalance due to secondary inertia forces by going with multiple cylinders. You can do that by going with multiple cylinders. That's the idea why we go for multi-cylinder engine. Do you get the idea why we are doing that? Now there's
Yes,
also
sir.
yes.
By keeping their like ignition at different times, so as to
Yeah, there
counter.
can a lot of things can be done. Yes, firing order, that is power impulses. Power balance will happen by keeping different ignition time. What you're saying is power balance, Aditya.
Okay, sir.
I'm talking about mechanical balance. So that's why I'm just now focusing on mechanical balance. I have not gone to the power balance yet. Okay. So greater the velocity of the piston, greater the inertia force. I'm sorry. So now force exerted during the top half of the crankshaft rotation is not equal to force exerted during bottom half of the crankshaft rotation. So this is a source of secondary imbalance in an engine, right? This is the source of secondary imbalance. And the primary imbalances are due to unbalanced masses, primarily in the rotating crankshaft, and are greater in magnitude compared to the secondary imbalances, right? So, so now how do we balance them? You consider a single cylinder engine. Are there any? Am I still connected? I'm just getting worried. My screen gets stuck. But I'm still audible to all of you, right?
Yes, sir, you're audible.
Yes, sir.
Okay,
Yeah.
I'm connected from two devices. I think the second one is giving some trouble. Okay, so now it's visible. Anyway, so when we go for multi-cylinder engine, I'll just give you one example. Okay, so then we also, this is mechanical balance. I hope you understand the difference between in mechanical balance. You understand the difference between what are primary inertia forces, what are secondary inertia forces, and what is static and dynamic balance, right? I hope these things are clear to all of you.
Yes, sir.
Yeah.
Yes, sir.
Good. So now we'll go to the second one that's called power balance. What is this power balance? So to give you exact definition, power balance, uh, power impulses occur at regular intervals and each impulse exerts the same force. So if power impulses occur at regular intervals and each impulse exerts the same force, then you can say that there is power balance in an engine. Now, is that clear now? What is power balance? So now consider just a single cylinder engine. Consider just a single cylinder engine. All right. What type of imbalances will be there? Is it balanced? How will you balance it? Can you just now, considering all this, whatever we have discussed so far, just consider a single cylinder engine. Okay, now we'll go one by one. What happens in a single cylinder engine?
So primary inertial forces are balanced, but not the secondary inertial forces.
Yeah, so mechanical balance. Let's not go to primary, secondary now. Even primary inertial forces is difficult anyway. So let's talk about mechanical balance and power balance. What about mechanical balance in single cylinder?
So it is not balanced.
Yeah, so you can say no mechanical balance. And what about power balance?
Sir, I
Yes, sir.
think power balance is there.
Yeah.
There is power balance.
Okay. Now you say that it happens at regular intervals, but it is how to put it. There is no overlap, right? There has to be power overlap. So it's not smooth, or I would say there is power at regular intervals, but it is not smooth. So to smoothen out, you have to have very large flywheel. So it's like this. There is irregular production of power which sets up vibration. It happens at regular intervals, but then the power is not good enough to keep the engine running smooth. So consequently, you have to have large flywheel. So you can say power. How to put it? Power production is irregular. Because once per every two rotation of crankshaft, correct?
Yes, sir.
That's how you get power. So there is power, and then the crankshaft has to rotate with the momentum. So you need a large flywheel. Why do you need a large flywheel? So as to keep up the momentum and to ensure you smoothen out this power. So you can say it is mostly not in use. Single cylinder engine is mostly not used, right?
So, but
Because
we
of
use
these.
a single cylinder engine in two-wheelers, na?
No, we do have, but even two-wheelers, I think now they would go for two-cylinder engines. You can check that, but that is quite small. So I think you can still manage it with a certain flywheel. So mostly,
Okay.
if you look at single-cylinder engines, they are extremely small single-cylinder engines in two-wheelers, where you're not dealing with very heavy. So even there, you need a flywheel which is large comparatively. We are talking about comparative, uh, you know, sizes. I think
Okay.
even two-wheelers are going for two-cylinder engines. If you look at some of the large CC two-wheelers, I think they use multi-cylinder engine as well, right?
Yes, sir.
So, but as the capacity increases, that is when the balancing becomes a problem, or we'll say mostly not used with large capacity. Let me add a qualifier there. So with large capacity, you can't use it. If it's just 100 cc, probably you can go with single cylinder engine with a certain type of flywheel. It can still be simpler. You understand?
Yes, sir.
So mostly not used with large capacity. Now,
Uh,
what about,
excuse,
yes, Abhilash?
Sir, here you mentioned that power production is irregular. Irregular in the sense, is it because we don't get some constant power? Is that the reason, sir?
Yes, yes. I have written bottom why it is irregular, right? So when I say irregular, I'm talking about this one. Once per every two rotation of crankshaft.
Yeah, fine, sir.
That's why it's irregular. So once the power is there, remaining, for one downward movement of the piston, you have power. Then remaining upward, downward, upward, the piston has to keep moving without any power. So that's what I mean by irregular. It is certainly in regular intervals, but there is no overlap of power. So, but when you go for multi-cylinder engine, you can have power overlap. You can have power overlap. Greater the number of... See, you should not have any stroke or any rotation of the crankshaft without any power generation. If that is the case, then you need the momentum to keep rotating the crankshaft. You need some momentum to keep rotating. We want to avoid that as much as possible. We want the crankshaft to keep rotating with power stroke from different cylinders. That will have a smoother rotation of the crankshaft. You understand what I'm saying?
So is that what overlap is?
Huh?
Is that what overlap is?
You
Overlapping.
you want to know what is the overlap?
Yeah.
I'll tell you. So, okay. So now we go for two-cylinder engine. So what happens in a two-cylinder engine? Let's say we have inline two-cylinder, okay? So you have to pardon me with the drawings. I'm just trying to draw something rough. How shall I draw this? So I'm just drawing a line diagram. So let's say this is cylinder 1, is the connecting rod connected to the crankshaft, and cylinder 2 connected to the crankshaft. Are you getting the idea? This is the crankshaft. Is it clear? The rotation of the crankshaft.
Yes, sir.
Yes, sir.
It's clear, right? I'm just drawing lines, I want to keep it simple.
Sir.
Okay? Yeah. So now you can see cylinder 1 and cylinder 2. So this is cylinder, sorry. So this is cylinder 1. This is cylinder 2. So now let me draw a simple table. It's there in the book, but I'm just trying to explain to you because just by looking at the book, sometimes it's pretty confusing. So now let's say cylinder 1 and 2. Okay, cylinder 1 and 2. So I'm calling it as revolution 1 and revolution 2. So consider cylinder 1. Now the piston is at top dead center, correct? Or let us start from, let us start with cylinder 1. Piston is at top dead center, right?
Yes, sir.
And then in cylinder 2, where is the piston?
Bottom dead center.
Bottom dead center. It's in BDC. Now, if cylinder 1 gets power stroke, okay, in revolution 1, if cylinder 1 gets power stroke, let me... when I say P, it's power stroke of cylinder 1. What is the corresponding stroke in cylinder 2?
Top dead center.
Hmm?
Top dead center.
Now, what is the stroke? So it will be compression stroke. It will move to top dead center. When you get a power stroke in cylinder 1, in cylinder 2 it will be compression. Correct?
Yes, sir.
Yes, sir.
So now after power stroke, what happens in cylinder 1?
Exhaust.
Exhaust.
No, cylinder 1 after power stroke, what happens?
Expansion.
Yeah, there is expansion. So how to put it? EX I cannot put. Let me put EP so that it is expansion. Okay. So when expansion is happening in cylinder 1, what is happening in cylinder 2?
Compression.
Compression is over, right?
Exhaust.
Huh?
Combustions.
Yeah, there is power, combustion, and then power stroke. It will move down because now expansion is happening in cylinder 1. That means piston in cylinder 1 is moving down. So obviously, what will happen in cylinder 2? I think it moves down. When it moves down, there is, combustion of gases. You can say power. Correct? Expansion and power at the
Sir,
same
power
time. Then
stroke
what
and
happens
expansion
after?
stroke aren't they?
Yeah.
Power.
Aren't they same, sir?
No. When I say power, it is combustion of gases. That is what is the meaning of power.
With the combustion gases, there will be expansion as a power stroke.
Oh, yeah. I think, no, I think I'm making a mistake. Yeah, you guys are right. Power means it is expansion. I think I confused the terms. Power means expansion. Okay. Power stroke means it is expansion. So when there is expansion, here there is compression. Right? After that, after power stroke, there is exhaust only. In cylinder 1, there is exhaust. And when there is exhaust in cylinder 1, there is power stroke in cylinder 2. Correct? After compression, you get power. So after exhaust in cylinder 1, what will happen? Again?
Suction.
Exhaust suction, sir.
Suction. So after suction, again, compression. Correct? So if you consider cylinder 2, there is compression, there is power stroke. After power, there is exhaust. And then suction.
Suction.
So this is the sequence. Are you, at least is the table clear to you, what I'm trying to write in the table?
Yes, sir.
So
Yeah,
you have
yes, sir.
cylinder 1 and 2. There is first revolution of the crankshaft, second revolution of the crankshaft. If you consider cylinder 1, in the first revolution of the crankshaft, you have power and exhaust. And parallelly in cylinder 2, you have compression and power. So now can I have another table for the same arrangement? Can I have another table for the same arrangement? So this I call table 1. So now let me write table 2. So cylinder 1, 2, revolution 1 and revolution 2. So now let me consider the same sequence for cylinder 1. P, E, S and C. So there is power stroke, exhaust, suction and compression for cylinder 1. So can I have another sequence for cylinder 2?
So starting with suction, we can do that. Cylinder 2 starting with suctions.
Cylinder 2 starting with suction?
Yes.
Sir, I guess exhaust, sir. We have to
Yes, sir,
distribute the
exhaust
powers in
type.
revolution 1 and revolution 2, sir. We got
No, I
revolution
think,
1, we got two power
see,
stroke.
when the piston 1 goes down, Piston 2 should move up. If you have power stroke in piston 1, you can't have suction in piston 2 because that means suction means it has to move
Fine, sir.
down. Both
Sir,
cannot move
if we
down.
see
Both cannot move
if
down,
we see
right?
the first one, sir, I mean, yes, sir. But in power stroke, we have to take exhaust stroke, sir. I
Yes,
guess.
exhaust. So it can
So
be
we
either
can distribute the
compression.
power stroke in two
Yeah,
revolutions.
you are right, Ajay. So it can be either compression or exhaust. That means what? The movement of the piston 2 can
Yes, sir.
either lead to compression or it can lead to exhaust. Right? You can
Yes,
have
sir.
that
But
combination.
exhaust is the best one, I think.
Now let's see whether we will find out whether which is best later on. So we
Okay.
have exhaust. After exhaust, what will happen?
Suction.
Suction. After suction,
Suction, compression, power
compression.
stroke.
After
Compression.
compression,
Power stroke.
Power.
right? This is what we have. So in these two, which is better now? So now I
Second
can
one.
time. Now
Second.
please understand. Now I can time my ignition in the cylinder accordingly. Correct? I can time the valve, camshaft, valve, and the ignition. Everything I can time appropriately so that cylinder 2 and cylinder 2, cylinder 1 and cylinder 2 are in this sequence. Either as per table 1 or as per table 2, I can time it accordingly. Correct? Can I do that? While designing my engine, I can appropriately design it so that these different combinations I can get. Correct or not? You guys
Yes, sir,
agree?
but I guess both are same.
Both are same in one
Both are
sense.
similar.
Both are similar. Why they are similar?
Because after ignoring the order, we will get power strokes. I mean, one after
The
the
power
other.
stroke
in
always
two
comes one after
pistons,
the
right?
other.
Yes.
The power comes one after the other. There is always two movement of the piston where you don't have anything. No power, right? So there also you see in revolution 1 you have power and power stroke. Here also at the end of revolution 2 you have power stroke for cylinder 2 and beginning of revolution 1 you have power stroke for cylinder 1. So still there is no complete power overlap. There is a, what do you call, irregular production of power again in two-cylinder engine. Are you getting it?
Yes, sir.
Yes, sir.
So now what happens if we go for four-cylinder engine? And how that will be?
We can get 4 powers, sir.
You will have 4 power strokes and then you can time it appropriately. So that
Yes,
means
sir.
for every, see the crankshaft is common, try to understand. The crankshaft is common, but you are going on increasing the number of cylinders. So now the crankshaft is going to experience more number of power strokes. Do you understand? If it is, see the same crankshaft, if I have only one cylinder, so the crankshaft will get 1 power stroke for every 2 rotation, 2 full rotation. So if you go for 2-cylinder, you will have 1 full rotation and 1 rotation will go empty for the crankshaft. But if you go for 4 cylinders, then the same crankshaft is repeatedly receiving power stroke. So there is an overlap of power. This is what I meant by overlap. Sangeet, are you getting what I meant by overlap? I think you asked it, right? What do you mean?
Yes,
by
sir.
overlap?
Now it's clear.
It's clear, right? So it's the same
Yes.
crankshaft. So now, let's say 1000cc engine. So now I can go with 1 cylinder which is of 1000cc capacity, or 2 cylinders with 500cc each, or 4 cylinders with 250cc each. Which is better?
Sir, 4 cylinders
4
with 250.
cylinders.
Obviously, 4 cylinders with 250cc each, because you will have more uniform distribution of power and then there will be power overlap. Though power from each cylinder will be smaller compared to a single cylinder, but then you have power overlap, which gives you smoother rotation of the crankshaft. So that is what I meant by power overlap. So anyway, I leave the 4-cylinder, 6-cylinder, 8-cylinder V arrangement as homework to you guys. Go and check that. Okay. But now you understood the concept, right? Why we are going for multi-cylinder engine.
Yes, sir.
Yes,
So
sir.
now try to understand, can I have different arrangement of this two-cylinder engine to get better balancing? Now this is two-cylinder engine. Can I have some other arrangement of this two-cylinder engine to get better balancing?
Opposed.
Yes, sir. Like upside down, sir.
Yes. Either vertically opposed or horizontally opposed. Then what will happen? Both of them will go to top dead center at the same time, and both of them will come to bottom dead center at the same time. Correct?
Yes, sir.
Now just imagine. 1 minute. I'll just show you. Now instead of cylinder 2 being here, if I have my cylinder 2 at the bottom, sorry. So if this becomes my cylinder 2, so you see when cylinder 1 goes to top dead center, cylinder 2 also will come to top dead center, correct?
Yes, sir.
So in both cases, you can now have, then what kind of arrangement you can have? Then the tables will be different now. So when there is power stroke in 1, you can also have power stroke in 2. Or when you have power stroke in 1, you can have suction in 2. Correct? So for this, I can again draw table. So now cylinder 1, 2, revolution 1, revolution 2. So this is opposed. So now if I have, sorry. So let's say I have power stroke in cylinder 1. I can have suction in 2. After power, what will I get? The same. Exhaust, suction, compression, correct? That sequence will be the same. So after suction, what will be there? Compression. After compression,
Or
power. And then,
exhaust.
Exhaust.
so now you see the power strokes are more uniformly placed.
Yes, sir.
I get the point now. If it is opposed, the power strokes are more uniformly placed now. I mean, you can have power occurring together at the same time, but this is a better arrangement. So you can have PESC for cylinder 1 and PESC for cylinder 2 also when it is opposed, but that is not a good power balance. But if you have this SCPE sequence in cylinder 2, then you have better power balance. Is that clear?
Yes, sir.
Anyway, so think about it. It's not sometimes if you don't understand, if you contemplate on it a little bit, you will get the idea. I'm pretty sure with this explanation you could have understood. Please key in your attendance. You can key in your attendance, and if you want to leave, you can leave now. And for those of you who may have some, did anyone find out the answer for tubeless tire?
Yes, sir.
Yes.
Yeah. What is the difference?
So they have something called like liquid sealant, so which prevent which allows the air to
What
go
is
out
that?
slowly. Liquid sealant, sir.
No.
So the sidewalls of tube tires are weak. I mean,
What is
they're
that?
not,
Tell me. Huh?
the sidewalls of the tire of tires. I mean, like they are not fixed compact with the rim so that they allow the air to escape from side.
Yeah, those are all there, but that's not the primary difference between a tube tire and a tubeless tire. See, obviously, tubeless tire, the strength of the sidewall is better compared to a tube tire. But that's not the reason. There is a big difference between tube tire and a tubeless tire.
For tube tires to prevent the bursting, the valve also escapes the air, sir, when
What happens
puncturing.
in tubeless tire?
In tubeless tires, only air escapes through the puncture point.
Why not through the valve?
Valve is fixed, sir,
Fixed where?
in tubeless.
Fixed in what part?
To the rim, sir.
Rim.
Yes,
In tube,
very
in tube,
important. Yeah, this is Jagdish, you are right. This is the big difference between tube tire and tubeless tire. In tube tire, the valve is fixed to the tube. You guys have seen, right? When you pull out the tube, the valve through which the air is filled, it is connected to the tube. So you can pull out the tube and the valve is connected to the tube. Whereas in a tubeless tire, the valve is not there because there is no tube. So the valve is fixed to the rim. The valve is fixed to the rim. So even if you pull out the tire, the valve is still on the rim itself. The valve is still on the rim itself. So how this enables, holding the air inside? Because the moment tube gets punctured in the tube tire, there is a gap between the rim and the valve, and the air escapes out through that. But whereas in a tubeless tire, since the valve is fixed on the rim, any puncture on the tire, the only way air can leave the tire is through the tire hole only. There is no other way the air can escape. So if it has to escape out through that hole, the back pressure holds the tire, and the loss of air from the tire is very, very slow because of the back pressure. It's extremely slow compared to a tube tire. In a tube tire, it can escape out through the gap between the valve and the rim. But here it cannot happen that way. That is why you still have some time before the tire becomes flat in a tubeless tire. And above that, you can have several other constructions like fluids and other things that some people are suggesting. So which can further enable the tire to run for a longer distance before it becomes flat. So anyway, I'm happy that at least some of you found out, and I'm quite happy that you are making some effort. That's good. So I hope now you understand the difference between tube tire and a tubeless tire. It will come when we discuss our chapter on wheels and tires. I'll again discuss about tube tire and tubeless tire. I'll give you the details. Okay. Okay, guys. See you then. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
sir.
Thank you, sir.
Bye.